Okay, good morning, ma'am. Good
Good
morning,
morning, sir.
everyone.
Good morning, sir.
So nice to meet you.
Same here, sir. Finally, we got the opportunity to interact with you.
Me too. Thank you.
Yes, sir.
I can see known faces. Mr. Dhruv Pandya, I know him. Uh, India Babaria. She's also a student here in the department, in physics
Okay.
department.
Okay.
I know. Javik, of course. I okay.
Preview. 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 Preview.
Yes, we can start now.
Preview.
Video. Learned speakers, invited guests, respected principal ma'am, dear colleagues, and dearest participants. A very good morning to one and all present here. The secret of getting ahead is getting started. With this quote, let us continue our journey of 2 days National E-Conference. Conferences are organized and conducted to gain insights, information that would remain effective to the audience. It gives me immense pleasure to extend you a very warm welcome on behalf of President Science College, who has clubbed all of us for the National Conference on recent advances and future trends in biological, chemical, and physical sciences 2021. We are here with the tremendous spirit on second day of the conference. Knowledge with action converts adversity into prosperity. This quote by Dr. APJ Abdul Kalam will come true for us as we walk through the next session of this conference. Let us have privilege to listen our eminent speakers. May I now request Ms. Krisha Shah to introduce our first speaker, Professor Pranav S. Shrivastav from Gujarat University. Trisha ma'am.
Thank you, ma'am. I, Krisha Shah, would like to introduce our first speaker of the day, Dr. Pranav Shrivastav. He is professor at Department of Chemistry, Gujarat University since January 2009. He obtained his MPhil and PhD degree in chemistry from Gujarat University in 1993. He has 28 years of teaching and research experience and completed 3 projects from SIR, DST, and BRNS. His research interests include bioanalytical investigation of drugs and their metabolites in early drug development phases. Professor Shrivastav has delivered 63 invited talks at various seminars, conferences, workshops in India and one in the US. He has authored 236 research publications in international and national peer-reviewed journals, guided 26 PhDs and 15 MPhil students. Professor Shrivastav has reviewed more than 540 research and review articles of different journals from American Chemical Society, Elsevier Science, Royal Society of Chemistry London, Future Science, Wiley InterScience, Springer, Taylor and Francis, and many more. He authored various chapters in national and international journals and have been editor on editorial board of Journal of Chromatography B, Elsevier Science, Journal of Pharmaceutical Analysis, etc. Now, I would request Dr. Shrivastav to take over.
Thank you. Thank you so much, madam, for the generous introduction. I'll just start sharing my screen. Hello and good morning to everyone. I am indeed very pleased and privileged to be a part of this very exciting 2-day nationally conference on recent advances and future trends in biological, chemical, and physical sciences 2021, organized by President Science College, Ahmedabad. At the beginning, I would like to express my deep sense of gratitude to all those who were behind organizing this e-conference. Shri Suresh Bhai Patel, Chairman of Sayona Group, Dr. Shivangi Mathur Ma'am, Principal of President Science College and also the convener of this e-conference. Thank you, ma'am, for giving me this invitation and opportunity to speak in this conference.
Thank you so much, sir.
Organizing secretaries, Dr. Jaivik Shah, Ms. Bindya Babaria, Mr. Dhruv Pandya, and all other committee members who are associated with this conference. Before I begin formally with my talk, I would like to echo the thoughts of our Honorable Vice Chancellor, sir, yesterday, when he mentioned the importance of multidisciplinary research, which is now the only way forward. We cannot restrict ourselves. And because of which, this seminar has even more relevance. Actually, translating knowledge gained in our classrooms into actual practice is the only way forward and is the key to success. In this, I'll just make it full screen. Yes, is my screen visible? Okay.
Yes, sir.
Okay. So, in my talk today, my basic intention is to bring forth certain recent measures which have been considered to assess greenness of analytical methods. The whole purpose of this talk would be focusing on what is green analytical chemistry, how it caters to sustainable development. And the second part would be, how do we assess greenness of methods? So these are the two parts of my talk today. Before I go on to explain what is green aspects of analytical chemistry and the methods of assessing greenness, I would just like to brief young students about what is analytical chemistry. See, analytical chemistry deals with material characterization. Basically, it is an information science, or we can also call it method science. It provides qualitative, quantitative information about any material which we find in this universe in any form. It can be in solid, liquid, or a gas. Analytical chemistry plays a significant role in our society, especially if you look at drug manufacturing, in process controls, in medical diagnostics, in fruit production, forensic surveys, and many others. It is a science, it is basically a science which is directed towards creating new knowledge so that we can improve how we work with our chemical analysis based on the increasing demands in chemical sciences. We know that we use a lot of instruments in analytical science, and that is mainly to assess purity, chemical composition, structure, and function. And of course, we work on very important parameters or factors such as sample preparation, which is an integral part and very important part of any chemical analysis, and based on which we come to know about the accuracy and precision of our method. So that is how, that is what we understand analytical science to be as of now. Now, if we look at the current trends in analytical science as of now, the last couple of decades have witnessed remarkable change in analytical instrumentation, basically in terms of technological changes. So this is where analytical instrumentation is heading, and that is where we find analytical science. There has been an increased applications of nanotechnology, automation, artificial intelligence, that has actually led to generation of very smart technologies, which are very robust, which are very fast, and at the same time they are accurate. However, the major focus in analytical science is towards miniaturization. Why? The reason is instruments consume considerable amount of energy. So, and if it involves a lot of energy, naturally it is taking something from this universe more. We are in the process of having, greening our methodology. So in that area, miniaturization is very important aspect, and this is where the trend is. Apart from that, we have automation, hermetization. That means we are not exposed to lot many things in front of an operator, and with the result that it leads to safety of the operator as well with automation. When we talk about hyphenation, where we combine two techniques, two complementary techniques, and they are done, this hyphenation or integration is done essentially to solve some very complex problems, real life problems. Basically, all miniaturization, automation, hyphenation or integration of equipments leads to green approach in analytical science. And that is where we are heading as far as analytical instrumentation is concerned. Now, coming to what is green approach in analytical chemistry and how do we understand this? We have some idea about green chemistry as such, based on the principles of Anastas and Warner. The whole idea of green chemistry has its roots in sustainable development. Though the initial attempts were directed towards, organic synthesis or industrial scale processes and products, as mentioned in the principles of green chemistry. Green analytical chemistry, when we talk about green analytical chemistry, that has emerged from the principles of green chemistry in the year 2000. It emphasizes basically on the role of analytical chemists to make laboratory practices more environmentally friendly. So this is one of the aim of green analytical chemistry, that how best we can make our laboratory practices more economical, sustainable, and environmentally friendly. Apart from this, we always, scientists always work on developing new concepts, and based on new concepts, they come out with new instruments or equipments which can cater to so many parameters of any analysis. So does it mean that we should stop, constructing new instruments? No. The purpose is to minimize or reduce the negative impact of any chemical analysis, so that we are able to save our environment and at the same time get the desired features from our analysis. All said and done, what we want here in green analytical chemistry is that we want quality results. We do not want any compromise in the performance of a method, but at the same time, we need to have environmental friendliness of analytical methods. And that is what we'll understand. What are those measures which we need to take here? Green analytical chemistry are those procedures which are of course environmentally benign and which are safer to humans. The greenness of analytical procedures here is a very complex phenomena. Why? Because see, in analytical chemistry, we do not have a formation of any product, right? Like, for example, in general chemistry or organic chemistry, what we find is reactants, they react to form a product. That means there is a change of mass. But in analytical chemistry, we do not have this kind of arrangement. We do not have any product formed. And when there is no product formed, there is no mass generated. So looking at this, how can we implement the principles of green chemistry to make our analytical chemistry green? That is what we want to understand. Now, if we look at the green chemistry principles which we all are aware of, as far as organic chemistry, synthetic organic chemistry is applied, there are only four principles which can be directly taken up from the principles of green chemistry. And those are prevention of waste, use of safer solvents and auxiliaries, design of energy efficiency. This is a very important aspect as of now. This is a factor which is being given due consideration in having principles for green analytical chemistry. And reduction of derivatization. Derivatization means you change the form of a substance such that it becomes easier for it to be detected or analyzed. So these are the 4 points which can be directly taken up from green chemistry principles into green analytical chemistry. Now this table gives us a first-hand information about what do we understand by green chemistry, and correspondingly what is there in green analytical chemistry. Now, if you look at on the left-hand side, there are 12 points which we all are aware of. And on the right-hand side, you will find the corresponding, principles which we have used in green analytical chemistry. And this is expressed through a mnemonic, that is significance. Significance doesn't mean any word, but it is a mnemonic because S stands for select, then integrate, generate, never, implement, favor, increase, carry, avoid, note, choose, eliminate. So based on which we have a mnemonic like significance. So out of this, what I've done is I've highlighted with the same color on both the sides, just to show you that these are the only 4 points from the 12 points in green chemistry which can be directly taken up in green analytical chemistry. Now, what are the key components of green chemistry, which forms actually the backbone of green analytical chemistry? The first one is the key: elimination or reduction of use of chemical substances. Elimination or reduction. Sometimes it is not possible to eliminate something, but can we do it with a very small amount, such as, like solvents and reagents and preservatives and additives for buffers, buffer solutions, so on and so forth. The second is use of environmentally friendly sample preparation techniques. My lot of emphasis would be on sample preparation technique because this is the key to the success of any chemical analysis. Because you get samples in this universe in any form, but they all come with a matrix. That means something which is not desired. And to remove it so as to make it suitable for direct measurement, you need sample preparation. And there are different approaches in analytical chemistry which work towards efficiency of different sample preparation techniques. I'm not going to highlight those sample preparation tools here, but I'll just going to mention the sample preparations which are encouraged in analytical chemistry for greening analytical chemistry. And those are ultrasound. Basically, in ultrasound, one uses high frequency acoustic waves to create microscopic bubbles in liquids. And with the collapse of these bubbles, shock waves are generated. And with the result, that solid gets solubilized in a suitable solvent. The other is microwave assisted extraction. This is also a well-known one. Then we have supercritical fluid extraction, where we use a different media, such as supercritical fluid, which is not a natural media, which one needs to create at a certain temperature and pressure. Then we have superheated water extraction, which is also a green approach in sample preparation. Plus we have many others like cloud point extraction, which doesn't involve use of any toxic organic solvents. We have solid phase micro extractions, which involves a single drop of an organic solvent for extraction. And then we use several special membranes for separating the analyte of interest from a given sample or a matrix. In addition to these two, we have what we require is proper management of analytical waste which is generated. Because of course, even though we minimize everything, our use of chemicals, etc., but still there will be some waste generated. So proper management of waste is also considered in evaluating method greenness. Minimization of energy. As I said, this is one of the major consideration is given to this aspect of how well we can minimize use of energy in our analysis. And of course, can we provide better safety to the operator in any chemical analysis? That means we can minimize risk of accidents. And basically, it concerns towards safety of the analyst or the operator. Now, so this was all about what I wanted to tell you in the first part. What is green approach in analytical science, what we look for when we go for greening any analytical method. See, why I'm emphasizing here on greenness here, I'll just like to share a few things. When we go for publications or research publications, most of us have seen that one of the major reasons for rejection of any method or any research article is novelty aspects. If you look at the reviews which have been done in the last 4 or 5 years in different journals from different publishing houses, one of the most principal reason based on which a paper is rejected is based on lack of novelty. Apart from many others, language and structure and organization and scientific content. The other thing which has now come into consideration and which would be implemented very soon is how green our analysis is, whether we are working with any kind of synthesis or we are working with any kind of analytical method development. So we need to show that our method is green, and in order to show that, we need to give some quantitative data, some quantitative information that how green our method is, not simply telling that it is green or not. So there are certain metrics which have been now well documented now in our literature. What I have done here is I have taken 6 of those metrics. These are the most important ones. My focus would be on the 6th one, that is AGREE, Analytical Greenness Metric Tool. However, I'll be just telling you briefly the first 5, what are they and what do they convey as far as greenness of any method is concerned. I'll start with the first one, that is National Environmental Methods Index, which we call as NEMI. Now this is one of the oldest tools used to assess the greenness of analytical procedures. This metric system is based on a simple pictogram, as you can see, which has 4 quadrants. Each quadrant represents some attribute, and that is, the first one is PBT on the left hand side, which is the full form for persistent, bioaccumulative and toxic chemicals. On the right hand side, you can see hazardous substances. So there is a list of hazardous substances which we have used or which one uses in a procedure. All those chemicals are listed in the Resource Conservation and Recovery Act, and they are categorized as D, F, P, U, and many others. There is a long list of hazardous substances which are being used. Then the other one is waste generated. This waste criteria is based on whether the waste produced is less than 50 grams or more than 50 grams in any process. And likewise, the 4th one, that is corrosiveness of our method. That is signified by the pH of our medium. If it is within 2 to 12, it is fine. Now, when we look at the color of these 4 quadrants, if the limits are above the prescribed limits, then it is left blank. That quadrant is left blank. And if whatever out of these 4 is below the limits, that is well within the limits, then a green color is assigned to that quadrant. Now, this is basically a qualitative assessment. It doesn't give you a quantitative assessment of greenness of your method, and therefore it is not in much use. You will find very less papers based on assessing any method based on NEMI, National Environmental Methods Index. Moreover, it is a time-consuming process because you need to identify the list of those chemicals which are hazardous. At the same time, there is no mention of energy, use of consumption of energy in a process. So this has limited use. The other one, the second one, that is analytical eco scale. Now this is an interesting metric where penalty points are assigned to the parameters which do not confer with the greenness of method, and that is based on it gives you a quantitative assessment. That means you assign penalty points based on the type of reagent used, the amount of reagent used. And see, if you can see in this table, you will find that how the penalty points go on increasing. If you use something less than 10 ml of your sample, the penalty points is 1. If you use within 10 to 100 ml, and it goes on increasing. Similarly, the level of hazardousness of your reagents which you use, and the penalty points you can see on the extreme right hand side is the amount of the amount corresponding to the penalty points and the amount corresponding to the hazards of using that reagent, and that finally gives you the total penalty points. And likewise, when we use equipments for analysis, how much energy is used in analyzing a given sample. If it is less than 0.1 kilowatt hour, then a 0 penalty point. And once we calculate all the penalty points and we subtract it from 100, that would give us the measure of greenness, how green our method is. We want as close to 100 as much as possible. Again, one of the some of the limitations are associated with this, that it doesn't consider all 12 points of green chemistry. So though it considers energy, but still it doesn't provide complete information about the structure of the hazards, and no information about the possible threats or the number of threats to an operator so that is how analytical eco scale metrics works. The third one is the multi-criteria decision analysis. Now, this is mainly used in environmental science and environmental management. Basically, it deals with social, environmental, economical, and technological criteria, especially during the decision making. Now, use of this metrics depends upon it depends upon the experience of an analyst, how well one can select. At the same time, it works on 9 different criteria. And here also, if you can see, there is no mention of use of energy in a particular analysis. And ranking is again based on Prometheus analysis. This is, I'm not going into the details of this because my focus today would be on the last one, that is agree, which is much simpler to understand, and it caters to all 12 principles of green analytical chemistry. The fourth one, this is also an interesting metric system that is known as GAPI, Green Analytical Procedures Index. Here, a specific symbol with 5 pentagons. As you can see, there are 5 pentagons here. And these pentagons have been further divided into 3 parts or 4 parts, right? And each of these pentagon represents some criteria of any analysis or methodology. As you can see, it gives due consideration to sample preparation, the types of reagents or compounds which are used, use of a particular instrument, sample collection. This is also very important: sample collection, preservation, transport, and storage. Because see, the entire workup in calculating greenness starts from sample collection. You go to a site, collect a sample. From that point onwards, till you get the final result, we calculate the method greenness. You can see in the center one pentagon, there is a circle in between that tells us that the method which we have used gives us quantitative information. And if there is no such circle in the center pentagon, it signifies that it is a qualitative method. We know there are two types of methods, qualitative and quantitative. Now, as I just mentioned here, these are 5 pentagons. Red signifies that it has very high impact on environment. It is not considered good. Yellow is somewhere in between. And green is the color which represents greenness. I mean, it is much better. And as you can see, this considers about 15 points, of course, 15 points. And if you can just look at these 4 figures here, all having 5 pentagons. One is having 4 pentagons. What you can see is the first one on the top, the penalty points are 52. And therefore, the score is 48. 100 minus 52. If you can just come down, you can see the score of 43. Penalty points are 43, and then the score is 53. And on the right hand side, you can find that the penalty points, as penalty points decrease, score increases. It is 69. And on the left hand side, one can very well understand what does this indicate. This indicates that the sample preparation was totally green here. So that is not even considered here. So penalty points are minimum here. As you can see, minimum red color in the pentagons. And subtracting it from 100, that gives us 85. The fifth one, that is RGB additive color model, red, green, and blue. Now, these are 3 primary colors. Now, this is a matrix which works on slightly different kind of assessment. It uses 3 different colors, 3 primary colors, which are red, green, and blue. Red signifies analytical performance. Green signifies safety and eco-friendliness, and the blue one represents productivity. And in between, if you can see, there are other colors as well: yellow, magenta, cyan, and white. So now these 3 major contributors will add up to give us the final performance or the final greenness of our method. Now the following slide will help us in understanding what does this indicate. If the satisfaction level, now this is not a highly quantitative method, but still, if the satisfaction level is greater than 66.6%, because there are 3 criteria, red, green, and blue. So then it is considered to be the final color of that method after synthesis would be white. And then therefore that method is considered to be a good method. When we look at the magenta color, what it tells us that one is, as far as performance is concerned, it is satisfactory, greater than 66%. At the same time, it is good as far as productivity is concerned, but it's not very good in terms of safety. So that is in between 66.6 to 33.3%. Now, likewise, if you go on to see, what you see at the bottom here is that if all the 3 are less than 33.3, then that method is not considered good enough to be used for practical purpose. And that is how you can see the color changes associated with this. Now, all these models, I have just described in short, they do not consider all 12 principles of green chemistry. But the 6th one, which I would be interested in discussing here today, is the AGREE, analytical greenness. Now, this is a very relatively simpler tool to assess method greenness, and there is a very simple software which can be easily you can download it, and you can put the required information, and you can automatically get a value signifying the greenness of your method. This metric system has been characterized through there are four aspects to it. One is comprehensiveness of the input, flexibility of the input, simplicity of the output, and clarity of the output. These are the fundamental things, and which includes, these 4 things include what is mentioned in this slide, which includes quality, quantity, and toxicity of reagents and chemicals used, number of procedural steps which are being involved in our analysis. This is also a very important part. How many steps are involved in our analysis? Requirement of energy, very important. Generation of waste, minimization of waste, how we manage that. Analysis of the safety of the analysis. This is also very important. Miniaturization and automation. So this is where I would be, mainly focusing my attention in this. This is, as I said, it's a very simple and easy to understand tool. And any one of us, if we know our method well, what we have done, starting from sample collection to storage to preparation to analysis to results, etc., one can use this. Now, in this metric tool, the input criteria is based on 12 significance principles. Significance, as I said, is a mnemonic, and are transformed into a unified scale of 0 to 1. That means each of the principles of green analytical chemistry is given a value from 0 to 1. 1 means it is good. 0 means, of course, as you can see on the right hand side in the figure, 0 means it is totally red, and green, 1 means it is totally green. So we always work towards achieving this green color. And if you can see this representative pictogram, you can find 12 numbers, 1, 2, 3, 4 up to 12. They all signify 12 principles of green chemistry which are applied to green analytical chemistry. Now, you can see some of them are a little wide and some of them are a little narrow. It signifies their importance. It signifies their importance in assigning these values to each of this. You can see some are green, some are dark green, some are light green, one is red. And after final synthesis of each point, there is you get the final result, which is mentioned in the center, that is 0.68. If this would have been 1, that means the method is totally green, which is rarely the case. But we need to increase it beyond 80, beyond 90, etc. Now, I have just put this slide again here, the same slide again here, just for you to understand what I said previously. What each of these principles, corresponding principles in green analytical chemistry, which are there in green chemistry originally. Now, the first principle. In this first principle, what is the essence of this principle? Direct analytical technique should be applied to avoid sample treatment, which says that it is better to avoid sample pre-treatment. Now, this is not always possible that you avoid sample treatment. If at all it is possible, because there are certain other techniques or tools in which we dilute and shoot. That is how the analysis is being done as of now at a certain level. Because as I said, it is not always possible to eliminate sample pre-treatment, because we need to convert the analyte of interest into a form such that it can be readily analyzed by any technique. But as such, what we can do is we can take a very small amount of sample and use as much less energy, number of steps, so that our analysis becomes more and more direct. At the same time, see, if you can see the first one, remote sensing without sample damage, that is assigned a score of 1. That means if without damaging or without workup with the sample at the sampling site, if you can manage that, a score of 1 is assigned. And as you go down, what you can see is when you look at a score of 0, what it tells is that external sample, you bring that sample to your lab, you pre-treat it, you make number of replicates and do the analysis. That leads to, that doesn't contribute towards greenness of method. Minimal sample size and minimal number of samples to be analyzed. Now, this is important. See, the number of samples can be reduced by using statistics for the selection of sampling sites, or maybe use of non-invasive methods for field screening. So if that could be done, number of samples could be reduced. For sample size, one can use ultra microanalysis or microanalysis or semi microanalysis as much as possible. That means if you work up till 100 mg, a score of 1 is assigned. But if you are working with a sample which is greater than 100 mg or 100 microliters, then one simply needs to put that value into the simple equation and get a corresponding score. So as the sample size, as you can see from this figure as well, as the sample size increases, the method leads towards more, less greenness. If you look at the third principle, this principle aims at the determination of target analytes as direct as possible. Direct as possible means you have to locate the device close to the measurement location. If it is possible to measure that analyte at the site, one can get maximum score. If it is an inline process where everything is done inline, there is a difference between inline and online. Inline means in a same set of things system, you analyze all the things. That means you do your analysis there itself at the site, you get the result, you get the output. That means you are just trying to use minimum energy, minimum steps without damage to your sample, etc. And as you go from inline to online to at-line and offline, you have different scores assigned to it. Integration of analytical processes and operations. Minimal use of reagents and energy. Integration of processes such as derivatization and extraction or chromatographic determination, pre-column or post-column. See, when we say about integration of processes, there could be something like this. If you analyze a particular substance in a given sample, if it is not possible for direct analysis even after sample treatment, what you do is you convert into a different form. For that, you can do it externally or you can do it online. So there are methods now where one can do this process online. So you avoid even number of steps. So less number of the steps you use in any analysis, greater would be the score. Automation and miniaturization. Now this is, as I said in the beginning, this is also one of the criteria. This is one of the trend now to use automated systems or miniaturized systems to have maximum greenness. And then as you can see, if you go with semi-automatic and manual and miniaturized, there are different scores assigned to it. Avoid derivatization. Now I was just mentioning derivatization before in the previous principle. In analytical chemistry, derivatization is commonly used as micro reactions. It is not done at a macro level. It is done at a micro level to improve extractability, analytical separation, and detection of target analytes. Now, it again boils down to something: how many derivatizing agents you use. So the score is, of course, given based on the type, the nature, the level of hazardousness of that derivatizing agent used, using this simple equation. Right? A score is 1 is given when no derivatization is used in our sample. So it is better to have direct analysis rather than derivatizing it beforehand. That means you are otherwise one is reducing the number of steps of analysis. Minimize analytical waste and have its proper management. This is also very important. Assessment is based on the following criteria. It is based on the amount of waste generated. If the waste generated in any analysis, in any one single analysis, is less than 0.1 gram or 0.1 ml, you get a score of 1. Otherwise, it all depends upon the amount of waste which is generated. And it can be easily calculated by simply putting your amount of waste in grams or ml generated per sample during your analysis, which one needs to calculate, and put that into this equation to get the final score. Preference for multi-analyte or multi-parameter methods. Now, it is advised. It is basically advised to have methods which can analyze several analytes at the same time. Basically, more number of consecutive analytes which are analyzed in 1 hour represents, this principle. If a number of analytes analyzed in 1 hour is around 70, a score of 1 is given. But generally, this doesn't happen in our routine exercise. But of course, as much as possible, we can work up to 10 analytes in 1 hour. And in between, one can always use this equation to find out what is our score for the number of analytes. I'll be taking a few examples also here at the end of this, all the 12 principles. Minimum energy requirement. As I mentioned here, they have classified 3 categories or 3 scores based on the energy consumption per analysis for sample preparation. Now, this is very important. Energy consumption, which is used for sample preparation, separation, and detection. So these are the 3 principal steps of any chemical analysis: sample preparation, then separation possibly through any technique, and detection. So based on the amount of energy which is used in all these 3 types of processes in any analytical system, a score is assigned for that based on energy consumption. Now, preference for reagents obtained from renewable source. Now, this is a new addition to what we were not aware of, that it basically wants that we use substances which are generated from renewable sources. So there is a list of reagents which one can refer to and see whether the reagents which have been used have any biosource. And this is based on a very simple, straightforward approach. If all reagents are bio-based, then directly a score of 1 is assigned. If some are bio-based, that means if you are using 3, 4 and 1 or 2 are bio-based, then of course you can directly put your value as 0.5. And if none of the reagents originate from biosource, then a score of 0 is assigned. Elimination of or replacement of toxic reagents. Now, this principle aims at removal of or replacement of toxic reagents by greener alternatives. Now, there is a list of greener alternatives which can be used as an alternate to the existing reagents or chemicals which we use. And for those procedures which do not consume any toxic reagents, a score of 1 is assigned. And for others, one can always use this equation. The best part of this green analytical tool is that it is software driven. You just need to put in your values in each of these principles, and then you can directly get a score for each principle. And once you are done with all 12 principles, you get a final score in a form of a pictogram. And the fourth one and the last one is the safety of the operator and environmental hazards. Safety of the operator is also given. That means basically it is encouraged for hermetization of the entire process. Which what I mean by hermetization is that one should be less exposed to different steps. So if all the steps can be done in a system, in a particular system, the safety of the operator is possible, and at the same time there are less chances of any accidents. And environmental hazards. Now, this principle takes into account the number of threats. See, I have listed here 7 threats: toxic to aquatic life, bioaccumulating products or bioaccumulating reagents which we have used, persistent, highly flammable, highly oxidizable, explosive, and corrosive. Now, these are 7 threats, right? If the threats is through your method is 1, that means if your reagents are bioaccumulative, that means you have 1 threat, then the score is 1 is given to you. So based on the number of threats from these 7 threats, one can very well calculate the score of your principle, of that particular principle. Now, the synthesis of all 12 principles comes out with a greenness score, ultimate greenness score. Now, this was all about what I wanted to tell you about the 12 principles, corresponding principles of green chemistry applied to green analytical chemistry. Now, using this green approach, what we tried to do was we tried to use this tool, this metric, to find out to what extent our methods were green. So this is some of the work which we did using supercritical fluid chromatography. Now, in this work, what we tried to develop is, we tried to separate 4 drugs. See, now, when you look at these 4 anti-diabetic drugs on the right-hand side, which are chromatographically resolved, you will not find all 4 drugs together anywhere in the market. What you will find is, you will find a combination of metformin, dapagliflozin, or metformin or empagliflozin, or metformin and canagliflozin. These are the combinations formed. So what our aim was, can we have more number of analytes in a single analysis so as to, of course, make our method more green? And that is what exactly we did. And in this study, we separated all these 4 drugs on a chiral column. I'll not be going into details of what exactly we did, but I'll just give you an overview of what we did here. And the mobile phase which we used here was carbon dioxide. So it is less toxic as compared to the conventional organic solvents which we use, along with methanol and isopropanol as co-solvents. And we calculated something about bond energies, the interactions, the energies of interaction the analyte with the stationary phase, etc., and then we applied computational studies to it. And then we tried to correlate how well our experimental results match with the results which were obtained from a software called Schrodinger. And we just tried to find out whether this elution pattern works, what are the energy considerations during this separation, and that is what we actually finally got, which were matching, both were matching here. Similarly, we went on to separate 4 stereoisomers on a chiral column, chiral 1H column here, and we were in a position to separate it. And then we again applied, we calculated the energy consideration, the entropy, etc., and everything was in agreement with the computational study which we did alongside it to support our experimental results. Even the order of elution were matching depending upon the number of interactions or the type of interactions of the analytes with the stationary phase material. And here we tried to separate 3 enantiomers of 3 drugs: etranolol, metoprolol, and antihypertensive drugs, and propranolol. And we could separate, see again, 6 analytes which we could separate within 6 minutes. So we just wanted to increase the number of analytes, we wanted to decrease the number of steps, and we could find out the greenness scores. Okay, I just forgot to tell you the greenness scores. The greenness scores here was 0.87. In the previous one, it was, I suppose, 0.88. And in the first one, it was 0.84. So that is what we did here. And in the last case, what we tried, is it possible to increase further the number of analytes? So what we did was, we tried to separate 15 analytes, 15 co-formulated drugs, antihypertension drugs, simultaneously, using a single elution protocol, single mobile phase. And we use a particular column, polyvinyl column here, vinyl pyridine selector column. And we use a linear gradient of carbon dioxide and formic acid in methanol. And this was possible to separate within 5 minutes all 15. So because of which the greenness, we could increase the greenness of our method, and that could be about 0.89, considering all the factors, all 12 principles. So that was all I wanted to share with you regarding green analytical chemistry. What I wanted to basically apprise you of what is happening in analytical chemistry and what is happening in this area of research, where how best we can do to make our method green, and some of the work which we did, and that is what we shared. And finally, this is a list of suggested reading which one can read to have more insight into these methods. But whatever I have spoken today regarding agrimetrics is a relatively simpler tool. It gives you a quantitative measure. So and one can very well when we start working with it, we are more cautious about which chemical to use and which not to use. And as a result, we can increase the greenness of our method. So with this, I conclude, and I thank you everyone for your patience, and I'll be happy to answer a few questions if you have.
Thank you very much, sir, for the informative sessions. Now I would like to request audience to ask questions.
Thank you. Okay. See, there are, as such, if somebody wants to refer to the list of green solvent, there is a long list of green solvents which are available. I don't have right now but there is a list of solvents which one can use. People have, for example, methanol is not, I would not say it's a green solvent. Acetonitrile, I would not say it's a completely green solvent, but it is much better than toluene and hexane and benzene, etc., etc. People have started using other ionic liquids as well, which are more green. But how far we can use them in a particular kind of work? For example, if I take this work, what we have done, it is not possible to use ionic liquids as of now. So there will be some it will not be a total green method when we talk about this, because we have not reached to a level where we can say that our method is totally green and we can use any alternate solvent. It is not possible. It is very difficult to replace, for example, here methanol and ACN, which we have used here. Of course, we are adding water to it, but as of now, nothing is can be considered as a complete green solvent. But there is a list which I can always share, which I don't have currently, but there is a list. But there is no solvent which is completely green as of now.
It's all comparative.
Comparative, yes. Okay, the principle of supercritical fluid chromatography. See, before that, I'll just tell you about what is chromatography a little bit for you to understand. See, the entire evolution of chromatography stems from the type of stationary phase which we use. We have been using silica as the base material for any chromatographic separation. And then we tried to use different kinds of moving phases. Liquid as the moving phase, gas as the moving phase. So when we talk about supercritical, now supercritical fluid is a moving phase, and based on which we have supercritical fluid chromatography. Now, what is different in this? See, supercritical fluid generated from CO2 is basically a state. It is not naturally available. It is a state which is which is obtained at a definite temperature and pressure. For example, if we look at carbon dioxide at temperature of about 31.5 degrees centigrade and 72 around pressure, atmosphere pressure, we get a state of CO2 which is different from solid, liquid, or gas CO2. Now, this state, what it does is, it is basically a non-polar kind of a thing, non-polar thing. So, since it is non-polar, it is difficult to elute anything from a stationary phase because it doesn't have elution strength. So, what we do is we add some co-solvents. Like, for example, what we added was isopropanol and methanol, so as to increase its eluting strength. So, if you ask me about the principle is of SFC would be that if you cannot do something with liquid chromatography, to a good efficiency. And likewise, if your analytes are not gases, you need an alternate solvent, moving phase. And in that case, we use supercritical fluid to make this separation possible, looking at the principles of green chemistry. I mean, catering to the principle of green chemistry, we move on to a different moving phase, which is much less toxic as compared to the solvents which we use in liquid chromatography or gas chromatography, to have better efficiency of separation and better performance. Okay. See, there are a list of techniques which I can share with you, starting from liquid extraction. I think most of us know it. Solid phase extraction. Then we have something called protein precipitation, solid phase micro extraction. There is a list of ultrasound extraction, supercritical fluid extraction, superheated water extraction, cloud point extraction. There is a list. I mean, if somebody wants to read, one can refer several books which are available for sample preparation, exclusively for sample preparation. There is a very detailed discussion on this. Every method has its own pros and cons, some advantages and some limitations. But my intention of telling you here in sample preparation as far as green analytical chemistry is concerned is restricted to ultrasound, microwave assisted extraction, superheated water extraction, cloud point extraction, and use of some membranes as well for separation, for extraction. Thank you.
Thank you so much, sir, for explaining the importance of green chemistry. And it sets the perfect example why do we need multidisciplinary research in science. We are indeed delightful to listen to your lecture, sir. Thank you so much.
Thank you, ma'am. Thank you so much. Thank you, everyone online. And thank you to all the participants. Thank you so much.
Very informative session it was. Thank you very much, sir, for sharing such precious knowledge with us. Next, I would like to call upon Mr. Piyush Menon to introduce our next speaker, Dr. Bishwaranjan Paital from Odisha University of Agriculture and Technology. Piyush, sir.
Thank you, ma'am. Good morning, everyone. I would like to introduce you Dr. Bishwaranjan Paital. He is currently working as the assistant professor in Odisha University of Agriculture and Technology. His major research areas are redox regulation biology and animals. He has 4 major research projects in SERP, DST, BPCL, and has 81 research papers, including publications of 2 books, 6 book chapters, 5 massive open online courses, amidst 4 fellowships with 11 years of teaching experience. He is the owner of 13 national and international awards. He has his membership in 17 editorial boards of journals. He is the managing editor in the journal titled Frontiers in Bioscience, associate editor of 2 journals named the Open Journal of Biomarker and Journal of Tourism and Hospitality. He is also the reviewer in 43 Thomson Reuters JCR listed international journals, also reviewer in 13 Scopus journals, reviewer of 3 e-book international publishers, and also has evaluated foreign master theses. Has also membership in 10 field of science researches. So I would like to invite you to share this session.
Now, before he starts, I would like to personally thank Dr. Bishwaranjan Paital for accepting our invitation. He's so humble. Whenever you meet him, you won't realize his scientific heights, and witty too. So thank you so much, sir, for coming here and accepting our invitation. Thank you.
Yeah, thank you. Thank you, Principal Madam, and thank you all faculties. And I should first thankful to all the organizers who have invited me to this wonderful talk.